Welcome back. Now we are into the 11th week of the course, and today we are going to start, as promised in the previous class, something very interesting, and that is we are now going to talk about energy balance with chemical reactions. So far, if you look into the discussion we had, we did not talk about any chemical reaction. And this part of energy balance is something very special to chemical engineers, as you can understand from the name, because as a community the chemical engineers only deal with reacting systems. So, for example, energy balance, this type of thermodynamics, mechanical engineers also do a lot, because they design turbines, wheels, engines, etc., etc. But there it is more like a change of phase is more important, right. So, you use superheated steam that has certain amount of energy, it has certain amount of enthalpy, right. So, it rotates a turbine, loses some amount of energy, transfers that energy to the turbine, right, and therefore, it becomes its degree of superheat reduces, its pressure reduces. But if you have looked into all the calculations that we have done so far using the steam table, there was no chemical reaction, right. And from our basic chemistry, we all know about chemical reactions. It is not that I have to teach you chemical reactions, and you are also educated enough to remember that there can be two types of chemical reactions, right, exothermic and endothermic. And what happens in exothermic reactions, heat gets released. So, the reacting vessel often becomes hot, and again, as a chemical engineer or as an engineer, it might be your responsibility to maintain constant temperature, so that there is not a overshooting of the temperature in these reactors. Why? Because if you do not take care of the heat that is getting generated, the reactor temperature will keep on increasing, right, and the biggest problem is that might actually lead to material failure. So, as I always tell, as an engineer, you must worry about the practical aspects. Therefore, often what happens, you see that there is a reactor which comes with a cooling jacket. In fact, I remember in the tutorial we took up a problem where it was very interesting that steam was used as the cooling medium, right. So, it must have been a very high temperature reaction. So, that heat needs to be extracted out. So, these are something that you will learn in your subsequent courses, maybe on process equipment design and reactor design and things like that. But more importantly, what exactly is happening in a endothermic reaction and an exothermic reaction, and we qualitatively know what is happening. So, in fact, this is the class we all look forward to, energy balance with chemical reactions. Right. So, typically you can write some reaction like this, and it can either be exothermic, where heat, I will not say heat gets generated, or the reactor or your beaker in which you have done all your reactions so far gets heated up. Other is endothermic, where the reactor gets cooled down. One can also write, let us say, a actual chemical reaction, let us say H2O plus SO2 leads to H2SO3 or something like this. So, how do we define, or how do we, let us try to understand what is exothermic reaction. Okay. So, what exactly is happening in exothermic reaction? So, you see the reactor gets heated up, right. So, in a reaction what you have the reactants, and you eventually results into products. Of course, there can be additional complexities that there is not 100% conversion, etc., etc. we will talk about that, we will learn how to handle those, right. Those are not big problems. So, why does heat get released, right? So, critical question to ask is, rather than just knowing that you have endothermic reaction and exothermic reaction, probably many of you know, but it is not a bad idea to ask the critical question, why heat gets released? And the simple answer to this is, the total enthalpy of the reactant is more than the product. So, essentially what it means, that more amount of energy was initially stored, right, energy in whatever form, energy within quotes. So, we will discuss how to quantify this. More amount of energy was initially stored in the reactants, and when the product forms, less amount of energy is stored into it. So, what happens? This difference in the total energy of the reactants minus the energy of the product, right, actually gets released, and therefore, your reactor gets heated up. This is essentially the physics of exothermic reaction. Question to ask is, how do we define this energy associated with each reacting species, right? There is a specific terminology for that, which we will talk about. And so, essentially what also is happening, you have the heat of reaction. So, what the energy, that is the energy change that takes place because of a chemical reaction, is what is known, I mean we will talk about the formal definition, is what is known as the heat of reaction, right. So, now what you can also understand, you can very well tell what happens in an endothermic reaction. Endothermic reaction, whatever is the energy that was initially stored, right, in the reactants, more energy is stored in the product. So, from where does this more additional energy come? This additional energy comes from the surrounding, and therefore, the surrounding medium becomes cold, right, in an exothermic, in endothermic reactions. So, how do we quantify what is exothermic reaction, what is endothermic reaction, etcetera, etcetera. So, in order to quantify that, we essentially need to define a parameter called heat of reaction. Typically, we define the standard heat of reaction, right, and it is represented as delta H R 0, right. So, what is standard heat of reaction? It is the, so when you are talking about standard heat of reaction, it is the enthalpy change associated with a chemical reaction at 25 degrees centigrade and 1 atmospheric pressure. So, loosely writing is equal to summation of enthalpy of products minus summation of enthalpy of reactants. Now, the question is, how do we write the enthalpy of the reactant or these products? And in order to do that, we need to define a parameter which is known as the standard heat of formation. This is a very, very interesting concept, because many of us often forget, and what is even more interesting, the assumptions associated with standard heat of formation. Because many of us, when we are talking about heat of reaction, we know loosely, we all know it is the enthalpy change associated with a chemical reaction, but we often miss out that this so called enthalpy change is defined or quantified in terms of standard heat of formation. And as you will soon understand, the standard heat of formation actually comes has certain degree of assumption. So, let us understand standard heat of formation carefully, and this will also allow you to learn about a special type of chemical reaction which is known as the formation reaction. Okay. So, let us see how it goes. So, standard heat of reaction is the enthalpy change associated with enthalpy change associated with the formation of 1 mole of a compound from its constituent elements in their standard state. At 25 degree centigrade and 1 atmospheric pressure. Now, this is very interesting. So, what it means is the heat of formation is essentially the heat of reaction associated for the formation of a particular compound from its elements in their standard state. So, the formation reaction of carbon dioxide, for example, so, typically we will write this and say, yeah, of course, carbon plus oxygen, carbon dioxide is getting generated. But remember, if you write this equation only, this is not the appropriate formation reaction. Why? Because there is a rider or specific condition for formation reaction, for a reaction to be considered as the formation reaction. The constituent elements must be in their standard state. Right. So, this is very, very important, and you specifically write therefore, in order to write a formation reaction, that carbon must be solid, oxygen must be gas, and carbon dioxide also must be gas. This must be written. So, first thing is the formation reaction is valid only for compounds, right. So, you can have only for compounds, right. This is number 1, and it has to start from its elements in their standard form. So, now the heat of formation data for carbon dioxide turns out to be, so this cap stands for molar, 1 mole, and the 0 stands for standard state, right. Typically, in principle, you can have this value also or this symbol also, but they are not same, because this is the heat of formation of carbon dioxide, right, but this does not specify standard state. So, you might independently does not specify standard state. You might independently write that you have done, let us say, the combustion reaction between carbon and oxygen at certain temperature and pressure, and this is the enthalpy change associated. So, you can say that at that condition this is the heat of formation, but that is not the standard value. The standard value which is accepted everywhere and you need it for calculating the heat of reaction, which you will also understand, is the heat of formation at the standard state, right. So, it is like this HF cap 0 for the particular compound, right. So, it turns out that the value of HF cap 0, so this is actually wrong and therefore, I will not remove it, but this will remain as something that is wrong, and this value turns out to be, as from the literature, it is minus 393.5 kilojoule per gram mole. So, this is analogous to as if 1 mole or 1 kilomole of carbon and 1 kilomole of O2 both at 25 degree centigrade and 1 atmospheric pressure are entering a reactor to produce 1 kilomole of carbon dioxide again at 1 atmosphere and 25 degree centigrade, and there is a reaction. However, the reactant and products enter and leave at the same temperature. So, some heat must get liberated, and that the amount of that heat is minus 393.5 kilojoule per gram mole. I am sorry, it should not be kilomoles, it should be 1 mole, kilojoule per gram mole, sorry, right. It is like this. Okay. There are certain riders in formation reaction. What you may please remember, a negative value of heat of formation means essentially exothermic reaction. In fact, this is not a convention. In fact, I must tell the full thing, we are still not discussed the heat of reaction in detail. Even for any heat of reaction, negative value means, right, negative value means exothermic reaction. And why is it so? It is because you see the way heat of reaction is defined. It is the total enthalpy of the products, right, minus total enthalpy of the reactants. And now, probably you can understand, once you already know the heat of formation. So, the heat of reaction is nothing but the summation of all the heat of formation of the product, standard heat of formation of the products minus standard heat of formation of the reactants. Okay. So, this is how it goes. Now, there are certain additional things you may want to recall, or you may want to remember or learn. The standard heat of formation for all elements in their standard state, this is extremely important, is considered or assumed to be 0. Now, this is something we often forget, right. This you must remember that whatever heat of reaction value or heat of formation value you are writing, this rides on this assumption. So, what does it mean? If you write something like heat of formation, standard heat of formation of carbon, which is solid at room temperature, it must be solid this is equal to 0. But please do remember, let us say or let us say heat of formation of oxygen, and it is a diatomic oxygen, which is the stable standard state, is 0, but this so what I have written. So, if you are talking about standard heat of formation of liquid oxygen, for example, it is not 0. Why it is not 0? Because liquid oxygen is not in its standard form. Similarly, heat of formation of O, for example, ion, that is not 0, right, because that is not in its standard form. So, any reaction that sort of, so this type of a reaction is known as the formation reaction, right, formation reaction, where we talk about the formation of a compound in its standard form at 25 degree centigrade and 1 atmospheric pressure from its elements, right, from its elements in their respective standard form, right, at 25 degree centigrade and 1 atmospheric pressure. So, this is what is known as a formation reaction, and the next example, very next example, gives you a very fascinating aspect about formation reaction. Let us try to write down the formation reaction of carbon monoxide. So, how will it look like? It will look like carbon in solid form plus, if you write stoichiometrically, half oxygen in gaseous form leading to CO in gaseous form, right. So, this is the absolutely correct formation reaction for carbon monoxide, right. But what is the problem? Problem is as follows: this reaction does not happen. Actually does not happen. Why? Because if in a reactor you take carbon and half the number of moles of oxygen, right, and react, you know what will happen? Half the amount of carbon will get converted to carbon dioxide, right, and the other half of carbon will remain unreacted, but you cannot get CO. However, that is not the consideration while writing the formation reaction. Formation reaction must be written in the form of the product forming from its constituent elements in their standard form. So, CO, the formation reaction is CO, whatever we have written is absolutely correct, and that tells us that the formation reaction may be a true reaction or can even be a fake reaction. This is very interesting. So, formation reaction may not happen, it might be a fake reaction, but does not matter. when you are writing the formation reaction, this is how it should go. So, one can write formation reactions, let us say, of several compounds. How to calculate these numbers? Well, it is a tricky thing. Heat of reaction you can in principle measure in a calorimeter. So, you can actually perform a reaction, and from there you can measure the amount of heat that is getting generated. It is possible. Now, you must remember, then in that case, to measure the heat of reaction using a calorimeter, right, the reaction must take place. So, therefore, the formation reactions of compounds that are true, the formation reaction takes place, well, they can be measured. They can be measured, but for compounds which have a fake formation reaction, it is actually a problem. And essentially, there are other routes to find out the heat of formation of such compounds following some other approach, or an approach called Hess law or Hess approach. So, that is something very, very important, and maybe I will start afresh in the next class, or Hess law as they call it. So, this is very interesting and is extremely helpful in calculating the heat of formation of compounds with fake formation reaction. And the list is pretty exhaustive. So, you can try to write down, for example, the formation reaction of H2O2, and it will be H2G plus O2G leading to H2O2L and stuff like that, right. So, quickly before we finish today's class, let us have a quick look at Hess law. So, what we have understood that this is a formation reaction of carbon dioxide and this is true. This is the formation reaction of carbon monoxide and this is false. However, another reaction takes place, and that reaction is oxidation of carbon monoxide. So, this reaction, this is not a formation reaction, this reaction can be performed and its heat of reaction value is known. So, what Hess law suggests, and I will pick up in the next class from here, that the heat of formation of carbon monoxide, or in other words, what it suggests is the whatever is the thermal heat change associated with the forward reaction, right, the backward reaction has exactly the same amount of heat associated with it with a negative sign. So, I will start from here. Let us not get into the details because we are running really out of time today, and from here we will pick up in the next class and show you how to calculate using Hess law. This is a very, very useful formulation, how to calculate using Hess law the heat of formation, right, of materials or compounds which have a fake formation reaction. And this concept we will extend in extracting heat of formation data from other reactions like combustion reactions or other reactions that might be happening. Thank you.